So we've spent a considerable amount of time now talking about the format and the setup of how to conduct a spectrophotometric experiment, specifically in the UV and vis ranges, or I guess more time is spent talking about those things. But I want to connect that back to the molecular level so that we can have that intuition of what's actually happening. And I alluded to this along the way, but I want to be a little bit more clear here. So what I have is a molecule. This is formaldehyde. And then I have the molecular orbital diagram, or part of it, for the formaldehyde molecule. It's not the complete MO diagram, but it is. It contains just the top 5 highest energy orbitals that include both the highest occupied molecular orbital, HOMO, and the lowest unoccupied molecular orbital, the LUMO. And so what happens is, when you shine light on this molecule, the smallest energy transition that can occur is going to be the one that's most available with the frontier orbitals between the HOMO and the LUMO. And so if you send in a whole bunch of white light, the exact frequency of light that matches the energy difference between the HOMO and LUMO is going to be the one that gets absorbed. And so that gets absorbed here, and then that promotes that electron to a higher energy state. And we call that an N to pi star transition, which we show here. The reason it's an N to pi star transition is it's just naming the orbital that we started with and the orbital that we ended with in terms of that electron. That electron is then going to fall back down, and it's going to dissipate energy in any number of ways, which I'll talk about in a little bit. Remember from Gen Chem, these notations just come from the symmetry of the orbitals and how they combine, the atomic orbitals and how they combine to form the molecular orbitals. So sigma has to do with a head-on type overlap, a direct overlap, and a pi comes from the side-on type overlap of the p orbitals that comprise those orbitals. And then N means it's a non-bonding orbital, and those are lone pairs on the oxygen. And so those are electrons that are not delocalized over the molecular orbitals on the molecule. Instead, they're just stuck right on that oxygen. So the lowest energy transition is actually this N to pi star, because that's the HOMO and that's the LUMO. And so what we see then is when we shine white light on this thing, it's absorbing in the region here. So we end up getting a band. This is the absorbance spectrum for formaldehyde. So one of the questions then would be, if this is a very, very specific frequency of light that gets absorbed, why do we not see a very, very specific frequency get absorbed in our absorbance spectrum? Why doesn't it look like this, like a delta function? Why is it this sort of broad function? And that comes down to knowing that what's really happening is not simply just the absorption of that photon, but there's a variety of transitions that are occurring inside of these electron transitions. So if you think back to several videos ago where I talked about inside of each one of these electronic transitions, there's actually several vibrational modes that exist for photons of lower frequency, and then inside each one of those there are these rotational modes. Then what you have here is excitation of electrons up to higher electronic excited states, but then it can land somewhere in the middle of a vibrational mode and a variety of accessible rotational modes, and the same can be true as it descends back down. And so what we have sort of built inside of this broad absorbance is multiple transitions that are vibrational and rotational in nature, and they sort of all blend together. The reason they blend together and why we can't resolve them, even if we had hardware that could resolve them, which we do, but even if you sort of had a really, really good monochromator that could disperse light down to, say, 0.0001 nanometers, you still aren't going to see these finely resolved features, at least in an absorbance spectrum, because these are, at least in this case, these are done in solution. And when you have molecules like formaldehyde in solution, these things are just bouncing off of each other, and they're colliding, and they're transferring energy back and forth and back and forth, and that's causing electrons in different states to absorb energy that isn't just from the photons. So it causes all this stuff to blur together, and we get this broadening. And that's why you end up with this sort of really wide, broad absorbance spectrum in a in a UV-vis type measurement. If you go on to do gas phase measurements where you can assure that the formaldehyde molecule is far apart from other molecules, then you can start to have fine resolution of vibrational and rotational modes. And this is an experiment that you often do in a physical chemistry course where you resolve the fine and the hyperfine structure of individual rotational and vibrational modes within small molecules. Typically you do this with carbon monoxide because it's really easy to see all these and it's not that complicated of a molecule. So the other question then is what happens to the energy when the electron ends up in an excited state. So of course energy has to be conserved, so the molecule can't stay in this heightened electronic energy state the entire time. This electron is going to fall back down. Where does that energy go? Does it get re-released? And if it does get re-released, in what form? Is that another photon? Is that heat? Etc. Okay, so let's think about what happens with the energy once an electron has been excited in a molecule. And so what we've got is a little bit more complicated diagram like this. Anytime that I have these sort of horizontal lines stacked vertically, we call these things Jablonski diagrams. I mentioned that in a previous video. Normally I just show one singular set of vertical lines or horizontal lines moving in one vertical dimension, and we just sort of have a singular Jablonski diagram. But we need to entertain the idea that the energy can move across different energy systems in the same molecule, and so that requires or necessitates some different descriptions here. Before I go too far, though, I want to clarify the difference in the type of electron excitation that can occur. And there's two states here that you see. One is called a singlet type of excitation state, and another is triplet. And so back with the formaldehyde, as I mentioned before just a minute ago, when you excite an electron from one state up to the next state by absorbing a photon, that electron has either a spin 1/2 or a spin -1/2. That's the spin quantum number of the electron. And it can preserve that spin up or it can flip and go through a spin flip. And what you end up with is either a state where you have spins opposed, which is normal, like this, and we call that the singlet state, or you have a spin parallel system where both in the original end state, that was an end to pi star transition, we have a spin up, and in the top we have a spin up. Those are two different states, and they actually require different energies to achieve these two things. You can see that the absorbance, one of them occurs at 355 and one occurs at 397. The reason for this manifesting this way is, again, beyond the scope of this class. This is the focus of a quantum portion of a PChem course. But it's important to note that they are two different types of absorption. And so what we're going to assume is that in this sort of bigger Jablonski diagram, the first type of excitation that occurs is the normal one. And in terms of these two things and competing with each other, it's a very, very, very small fraction that ends up in the triplet state. The vast majority end up in the singlet state, almost imperceptibly so in the triplet state. And that makes sense because if you think about formaldehyde, it's a colorless solution if you've ever seen it before. It's not colored. And that's because its primary absorption is in the UV. We can't perceive that as color. If the triplet state were actually dominant, then we'd see this as a colored substance because this is in the sort of far violet, but still perceptible typically by most humans. So let's start here, where it says start here, ground electronic state. This is, you're just assuming you've got electron here. You absorb light, and that occurs in this absorption step. And so the vertical line here, the straight line, refers to a photon transition, and the squiggly line refers to a non-photon system, meaning it's not absorbing a photon, and it's not releasing. It's transferring energy in a different way from across those energy levels. So the very first thing we're going to look at is this vertical line here, which has A, and the reason it says A is because that's an absorption step. that is the phenomenon we understand as absorption. But know that when you absorb a photon of light and you excite a molecule's electron from a ground state, in this case the ground state for formaldehyde would have been in the n molecular orbital, the non-bonding orbital. You excite that up to the next, the first excited state. Then it can land anywhere inside of those different vibrational modes. Each of these sort of smaller lines that's clustered together, those are all still within the n equals 1 excitation, electronic transition state. And then subdividing inside of that are all the vibrational levels. And then not shown here are all inside of those a similar set of stacks, but really fine, which would correspond with those rotational levels. So we send this electron to an excited state and it lands right here, which is in not just an excited electronic state, but also an excited vibrational state. So it's in the n equals 1 electronic, or I'm sorry, this is actually the n equals 2, because this ground state would be n equals 1. So this would be the n equals 2, the first excited state, but it also a vibrational state. And so in terms of answering the question, what can the molecule do to release this energy to conserve energy, it can do a couple different things. So one of the things that it can do is it can just sort of vibrationally relax. So as the electron gets excited up to here, right, it absorbs that photon. That's an electronic transition, but it also stimulates whatever vibrational mode that is. So it starts vibrating rapidly based on whatever mode that is. If it's a symmetric stretch or an asymmetric stretch or a wagging or whatever the mode is. One thing that it can do is this R1 transition. And the name's not important, but the concept is. And the squiggly line here means that it's not a photonic transition. This is a thermal one. And so it just relaxes and releases this amount of energy wherever it started down to this point by just vibrating and colliding with other molecules near it. And so it's releasing that energy thermally through vibration and friction. And so what it can then do is go through this process called internal conversion. And internal conversion moves it over to a whole nother set of modes here that run all the way down to our original state. Notice that in our first sort of transition, there's a big gap there where there's no energy states, meaning the excited electron can't traverse through here. At least it can't stop at any waypoints along the way because those aren't defined. Those aren't viable states. They're not defined. But what it can do is go through this internal conversion method, and then it just relaxes all the way back down to the ground state. And in doing so, this gets released as heat from the system. And that's one way that the original energy of the photon gets conserved in the molecule as it relaxes back down to the ground state. Okay, another type of transition that can occur is one that you're all familiar with, but maybe you never thought about it. So you have your first excitation, which means it ends up somewhere up here in the n equals 2 electronic state, but also it's in a higher vibrational state, just like we said before. And then it goes through this R1 relaxation. So it releases a little bit of its original energy in the form of heat. So the original photon had this much energy, the full length of that straight line, and then it loses some fraction, R1 here, we subtract that from the original energy of the photon, and then it can go through a direct transition. Instead of going through this internal conversion, it can go straight from the bottom end of the vibrational modes of the n equals 2 electronic state, and it can transit all the way back down to the ground state. And in doing so, if it goes through this process, it is going to re-emit a photon of light. And when it re-emits a photon of light, we call that process of emission fluorescence, which we've all seen before, right? Some places that you might have seen this are with these kitschy black light posters. So how do these things work? Well, they're made up of dyes that specifically undergo this fluorescence process. You take a UV light source, which we call black light, which is funny. Let's see if I can change the color. So black lights aren't really emitting UV, but they're emitting violet light, so it's really close to the borderline of what we can see. So high energy light. So you get UV light, and that shines on these dyes, these molecules that comprise this poster, and you get absorbance of those dyes all the way up to this excited electronic state and the excited vibrational state. As long as it's in a higher vibrational state as well, a fraction, some amount of that energy of the original UV photon, or not UV, but violet in this case, photon, is lost simply to heat as those vibrational levels relax back down, and then the photon is re-emitted back to you in the form of these colors. And so you shine a high energy photon, which is violet, and what you get out of that are lower energy photons based on fluorescence. So fluorescence is always going to release a photon that is a longer wavelength or a higher energy than what, a lower energy or a longer wavelength than what you put in, simply because you've lost some energy to this step here. That's what fluorescence does. Fluorescence occurs on a really fast time scale. So from the moment that a photon is absorbed, another photon is re-emitted anywhere from about 10 nanoseconds up to about 0.1 milliseconds. So a really pretty rapid process. So goes up, comes back down, and it vibrationally decays really quickly and pops another photon out in a really, really fast way. That's what fluorescence is. Fluorescence is really nice as an analytical tool, as we'll talk about in the next video, in that you start with some lamp that is a particular wavelength that's much higher energy, and then what you get are new photons that are re-emitted that are lower or lower in energy or longer in wavelength than what you started with. And so the detected photons are distinct from the input photons. And so there's not this background masking it, where you have some of your input signal that's the same as your output signal and they look the same. That makes it difficult to differentiate the two between these photons when you're trying to measure a really small signal. We'll talk about that in a second. So let's think about other options here. So another thing that this molecule can do, so let's start back at the ground state, it absorbs that photon, it ends up at this singlet state. What it can do is relax back down through R1, but instead of going the internal conversion route, instead of going the fluorescent route, it can go through this whole process called intersystem crossing to T1, which is essentially means that the spin flips on that electron that's been excited, and so now you have spin parallel states, which is more or less a forbidden state. It doesn't happen very often, and so this process is considered forbidden, and by forbidden in spectroscopy sense, it means that the distribution, the probability of this happening is very, very low based on the symmetry of events, etc. And so I'll leave that to the math for you to describe if you take a PChem course. And so what's interesting here is now we're in the triplet state. So imagine we excited the electron, it's up here in the singlet state in this purple line, it then decays through this R1 mechanism, then it goes through this intersystem crossing, so it's in a whole new set of energy levels defined by the triplet state because of that spin flip in this forbidden mode. And what it does then is it proceeds, if it ends up here through this intersystem crossing, it then relaxes itself through all of the vibrational levels until it ends. And there's no more vibrational levels to relax through, and now you have this big void here between the bottom of this set of energy bands and its ground state. So what it does is the electron then relaxes back down all the way. In doing so, it re-emits another photon. Not another photon, a photon, if it proceeds through this method. This type of photon emission gets a name called phosphorescence, which is distinctly different than fluorescence in that it's fundamentally different in terms of the energy states that the electron transits through. In this case, it goes through this forbidden triplet state, and in doing so, because this is considered forbidden, the process takes much longer. So if you look at the time scale that phosphorescence occurs over, it's on the sort of where fluorescence leaves off. The longest type of fluorescence is where phosphorescence picks up, so about 1/10 of a millisecond, and up to hundreds or even thousands of seconds for certain phosphorescence. So you've probably seen this before too in products that you're familiar with. So if you have really any glow-in-the-dark toys that don't have an active emitter in them, meaning they don't have a battery pack and then a light that's actually causing them to be glow-in-the-dark, but they're just genuinely a solid-state object, like these stars that were really popular. I don't know, they might still be popular, but they were popular when I was growing up. You put them all over your room, and then the light from the natural light of your room or the sunlight would cause these things to charge up, and by charge up, what's really happening is they're absorbing photons of light. They're going through this R1 vibrational relaxation. They go through an intersystem crossing. They go through the R3 relaxation, and then by the time you shut off the lights, that phosphorescence timescale, because it's so much longer, it no longer needs an active input of photons to still be releasing photons, because it's releasing photons from several tens to hundreds of seconds before. And that's why these things didn't last for very long, right? You'd have to keep flipping the light on and shutting it off, flipping it on, shutting it off, or you'd take a flashlight and you'd shine it on a star and it'd be really bright for a little bit, and that's because you populated a lot of electrons into this state, and then they decayed over whatever their phosphorescence decay time was. Same is true for if any folks have grown up on the West Coast, you might have seen this stuff called phosphorescent algae. So phosphorescent algae, at least on the United States West Coast, it could, I don't know, it might be a global phenomenon. Well, I imagine it is. But this stuff, when I used to live on the West Coast, we would see this periodically where you have algae that actually have dyes that are created inside of them. I have no idea what the evolutionary reason for that is. You could probably look it up. But these things essentially absorb light during the day, and then as the light goes out, the algae starts to glow overnight, and it's really the glow mechanism is due to phosphorescence and the delayed re-emission of photons that were absorbed earlier in the day. Which is this really fascinating phenomenon. So I show you these things to give you a sense for what's happening in a molecule, because I think it's really amazing. This isn't all of the stories. This is only part of the stories, but I also want you to understand, because every one of these mechanisms here, absorbance, fluorescence, and phosphorescence, all of these things are possible analytical signals that we could leverage to measure something. And there's techniques associated with everything, and fluorescence being a really popular one, especially if you're in the bio world, simply because it's super sensitive, and I'll tell you why in a second. Before I do that, I want to show you I want to make it a little bit more complicated, in that these Jablonski diagrams are all just sort of two-dimensional representations of the energy states and the energy transitions in a molecule, but really the way that we should be thinking about these are three-dimensional surfaces. And what I have here is just something I grabbed off the internet. But what you have are ground states that aren't flat. They depend on how the molecule has vibrated in space and how it's oriented or rotated in space at that moment in time, that you can have different surfaces. Your electronic states have different contours, and so you can look for the sort of global minimum, which would be the shortest distance between those two planes, but know that that's not a fixed number. That's a functional number depending on exactly the nature of that molecule. And I alluded to this earlier on when talking about in the early part of these Chapter 18 videos, that this is largely where we are as scientists in understanding molecules, in that we're mostly not shining continuous wave photons onto molecules and looking at steady state processes, mostly to understand fundamental aspects of molecules, that is. But instead what we do are shining pulsed photons. So maybe we're only illuminating that molecule for a picosecond or a femtosecond or an attosecond, in which case the time that it's illuminated is on the order of one of these processes, either absorbance, fluorescence, or phosphorescence. Phosphorescence is certainly easy to do because that's such a long process. Fluorescence is pretty easy too, because that's even tens of nanoseconds. But the absorbance process and what the electron dynamics inside of a molecule when it's undergoing an excitation or when it's undergoing a singlet to triplet transition, those are now monitored with these time-resolved type spectroscopies. We're not going to talk about it in this course. You'll never talk about it in an undergraduate course because it's something you wouldn't get to unless you did a PhD in physical chemistry or applied physics. But I just want to give you a sense for, I think, the beauty and the complexity of molecular systems and how much we've actually learned about these things. Nobel Prizes were given for femtosecond spectroscopy. I don't know, it's probably 10 years ago now, simply because developing the tools to send femtosecond packets of light, it's really hard to do. One more thing that I want to mention is that glow sticks, you've all seen glow sticks before, these are neither phosphorescence nor fluorescence. This phenomenon that you see comes from a process called chemiluminescence. Chemiluminescence is a specific flavor of emission, luminescence really just being re-emission of photons. But instead of this being a re-emission because following an absorbance event, glow sticks work in the absence of any light, right? You can be in a dark room and these things never having been exposed to light, but they'll still glow once you crack them open. And that's just simply because you have some molecule A plus some molecule B, and in their reaction, they create an excited state of one of the molecules. That excited state, B, or B star here, then relaxes down to B, and that energy difference from the excited state is coincident with some transition, like a fluorescent transition, so it emits a photon. And so it's different here in that it's chemiluminescence. If you remember back to the electrochem chapter, I showed you some of the research that I do in my lab, and we developed some reactions that are electrochemiluminescent. And that takes it a step further, where this transition here, A plus B to an excited state, is an electrochemical step. And so we can pump an electron into a molecule using a voltage, create an excited state, and then have that decay back down. And that's the basis of some sensors. Okay.